Continue. So the next step is about the Juicy-Murphy elements and the Murphy basis. So as we've just discussed, up until A5, I managed to compute all the decomposition multiplicities by hand. I had a very long train journey through all of Germany, from east to the west, and so I was jet lagged. I needed something which was not too difficult, but still enough to keep me awake, so I computed all of those. But if you want to somehow do the general case, you need some more powerful tool. There are some good ideas which come originally from the study of symmetric group and Hecke algebras. So they've already been applied in similar situations. It's, I think, by now quite standard techniques. So I've seen this in Brouwer algebras and related stuff by a number of people. So I'll just mention some names of people who develop such ideas. So I think all these people and more would be underwhelmed by this section because I've done things in a very similar setting. But unfortunately, one can't just apply the result, needs to somehow mimic it in this setting. So that's what I'll do now. So the Juicy-Murphy elements. I'll call them x1, x2 up until xr. There's some elements in AR. X1 is the easiest one, it's just 0. It's just convenient to add it on anyway for some statements, otherwise it would be slightly less pleasant, but so it's just 0. X2 is given by the sum of two diagrams. Where just we take a crossing in the first two dots and then just straight lines afterwards, and we add on something similar but just a cup and a cap in the first two dots and just straight lines afterwards. And then also give x3, then hopefully the pattern becomes obvious. So now we take a crossing in the second and third position and do also a cup-cap combination in those two positions, but then we proceed by also adding on this crossing and this cup and cap. So here we do something in position 1, 2, and here we do something in position 2, 3, and 1, 3. And then we just carry on similarly. So for those who are familiar with the Juicy-Murphy elements for the symmetric group, if you just ignore the diagrams which have cups and caps, you get the ordinary Juicy-Murphy elements. So somehow, to get the right thing here, you need to add on something. And then the following fundamental lemma for the Juicy-Murphy elements is that xi commutes with the subalgebra AI minus 1 inside AR. So yesterday we fixed an embedding of any smaller paraplectic Brouwer algebra in AR. So it's just concentrated in the first I minus 1 positions. So if you take that subalgebra, it commutes with the corresponding Juicy-Murphy element x and I. And of course, xi itself is contained in AI. which means that in particular all the juicy Murphy elements together generate an abelian subalgebra. Because there's a special case of this statement, xi commutes with xi minus 1. So it's, of course, in general quite useful to have some big commuting algebra inside your bigger algebra when you want to compute decomposition multiplicities. So I think, but yeah, maybe we should have checked. For the symmetric group, this even generates the center, or at least it's a maximal abelian. Yeah, it shouldn't really be the center. But maximal abelian, that's it. Yeah. But there is some way to construct the center out of them, I think. Symmetric polynomials, etc. Yeah. Okay. So. Next step is the Murphy basis. So that's the basis of the cell module. So to construct this basis, we just need to make the following observation. There is some short exact sequence of the following form. We start by all the summation over all partitions of the following form. So we sum over mu for some fixed partition lambda, and we have a direct sum of cell modules for a r minus 1. This forms a submodule of the restriction of the cell module for AR to AR minus 1 corresponding to lambda. So it's a short exact sequence related to this cell module for AR, which we view as a module over AR minus 1. And here we get something similar, but here it's all partitions which are of size 1 bigger than lambda and which contain lambda. Of course, for this one to make sense, we also need to assume that this value is still, or at least is smaller than r minus 1. So if I would have taken a partition lambda of r, somehow the extremal case, then this term would drop out. So that's something which is not too difficult to prove. I mean, it's easy to kind of intuitively see why such a thing should be true. If we think about the standard module for the CR algebra that we had before. So it was something like this, and then we add on all the n minus diagrams. So then we take the Shor functor and only keep diagrams which end in the maximal amount of dots. So for instance, if lambda would be a partition of r minus 2, we would get all diagrams of this form. And then we restrict to r minus 1. So if we happen to restrict a partition like this, a diagram like this, and regard this as an element of the AR minus 1 module, it looks like you might as well pull this line here and see that this has a module which is induced from a symmetric group representation of a bigger symmetric group. Just the tensor, the exterior tensor with the trivial module, or just the induction to a bigger symmetric group. And then we apply the well-known rules, the Littlewood-Richardson rules, which tell us what simple modules appear for the bigger one. So these are all these ones that appear. On the other hand, if we would have looked in the region or at the space spanned by diagrams like this, and then we restrict, that it's as if we were restricting the symmetric group module. And then we applied the Littlewood-Richardson rules for that, for restricting a symmetric group algebra module to a symmetric group one lower. And then you get precisely these ones. So it requires a little bit more checking, but that is really what is happening. So somehow this corresponds to all diagrams which end in a cup or in a propagating line, and then you do some manipulations to get this thing. So it's nothing too deep, this observation. But it is useful because it means we can somehow canonically construct a basis iteratively. Actually, the reason we have this nice relation might be the true reason why these cell modules are interesting to study. Because for simple modules, we couldn't have such a nice expression. But for cell modules, there's somehow a very close connection between the cell modules for the bigger and the smaller algebra. So I would say this is the analog of translation of Verma modules. So if you translate a Verma module, you know more or less what you're getting. If you translate a simple module, you need to work in order to find out what it is. So that's the same thing here. We want to understand the simple modules. Well, we start with the cell modules, we restrict, we know what happens, and then we work our way back to the simple modules. So it's a very close similarity, and it's actually also more than just a coincidence. There's some true connections for this. Between this restriction functor and the translation functor for the paraplectic Lie superalgebra. But for now, it's just a philosophy, let's say. So this observation allows us to define a basis for this cell module, because if we have a basis for the cell modules for AR-1, this kind of gives us a canonical choice for a basis for that one. We just take the basis of this, and we take elements in the pre-image of the basis element of that, and we construct some basis for that cell module. So that's then what is usually known as a Murphy basis. So the basis elements are labeled by T belonging to some set, which I write like this for now, ST R of lambda. And this set is given by sequences of partitions, which start with the empty partition and end with the relevant partition there. Sequence of R+1 partitions. And in every step, every partition is obtained by the former one by either adding or removing a box. So that's of course based on this observation here. Either we remove a box or we add a box, and then we restrict further. Again, either we add or remove a box until we reach A1 or A0, which only has the empty partition playing a role. So one common way to think about it is, first I should say, maybe the reason I took this notation is in case it happens to be so that we take a partition which is actually of size R, then we don't have any choice. We need to add a box in any case. And then that actually corresponds canonically to standard Young tableaus by just keeping track by writing the number in each box that you add of the step that you take. So if lambda is equal to r, then str is really just st of lambda, which is the state of, or at least isomorphic to the state of standard Young tableaus. Of shape lambda. Which of course naturally labels the Murphy basis for the symmetric group. But here it's something slightly more general. I think one useful way to think about it is as paths in a Bratelli diagram. So we have the following diagram. No, can't go there. Was a bit too quick there. So I think now it's still doing. So I want to draw a line between any partition which corresponds to adding or removing a box. I think this one is missing. Yeah, thanks. Okay, so the elements of that set correspond to paths in here. So I always start here and I just take some path towards the partition that I need to end in. So some notation. So for such a path, I'll write its elements as T0 up until TR. So these are all just the partitions. And T prime, if I just remove one, the last partition in the sequence. So this is an element of ST R minus 1 of T R minus 1. And we have some partial order. Which is defined as follows. It's defined iteratively, but it's or lexicographically. So it's I say that. Sorry, that doesn't make sense. So I look at the last two partitions in the sequence, and I say that bigger partitions of bigger size or smaller. And if the other possibility that I get a relation is when the partitions are actually the same. And then I just remove them, and I need to have a relation between what is left. So for two sequences to be comparable, they need to be the same up to some point, and in the first point where they're no longer the same, one has a partition of bigger size than the other. Yes?
Yes, so the first one.
No, there's a relation either if one is of strictly bigger size or if they're the same and something.
So the best components should be like that, no?
Yeah, I see. Yeah, so I also compare stuff for different lambdas. So one would be in str lambda and one would be in str mu. Yeah, that's a good observation. Of course, S would be in there. I mean, I'll only need to compare for the same, but then I would kind of automatically skip this step, and I would start at r minus 1. That would be another option. Yeah. Yeah, might have been better to introduce it as you suggested, because I'll only need to compare things in the same set str lambda. But yeah, one can extend relation to arbitrary paths, of course. So I have juicy Murphy elements and a Murphy basis, and now I want to mention what happens if I act with the juicy Murphy elements on the basis. So we've seen that XR commutes with the subalgebra AR minus 1, which means that I have an action of XR on the restriction of a module which commutes with the action that I keep on R minus 1. So that space decomposes as a module into possibly generalized eigenspaces for XR. So for instance, if I take some module here, then it will be inside an eigenspace for XR. And here it will be generalized eigenspace in general, because it could be mapped to something there. But so that means that I will have a nice action of the juicy Murphy elements on the Murphy basis. Because I have these commuting actions, and the Murphy basis is precisely obtained by restricting in that way. So they will be generalized in general, because this thing was a short exact sequence. Yeah. I mean, most things will split, but something won't. So if we take some lambda in our set of partitions, then some path in the corresponding Bratelli diagram which ends in that partition. You will get an action of any juicy Murphy element XL, so L ranging between 1 and R. And that action somehow corresponds to the smaller L is, the more times I restrict before I look at the action, you could say. So, because it's in the smaller subalgebra, it's only the restriction which is relevant. So, what you will get is some constant, some constant depending on L and T, and the same element, up to some things, some basis elements, which correspond to paths which are strictly bigger. So some terms corresponding to bigger paths. So that corresponds precisely to the, because the order on paths we took was really related to this short exact sequence that we had, which was based on whether a partition was of a different size or not. And that constant is given by the following. So it is a content of some box, if that is the box that we add in the L step. Or it is a content of a box plus 1 if we remove a box. So in each step of our path in the Bratelli diagram, we either add or remove a box. And these values are related to that. So I'll just recall what the content of a box is in this case. And then I'll do an example to make it a bit clearer. So in any partition, or more precisely in the associated Young diagram, we have a standard content for each box, which is 0 for the first box, and then when we move to the right, we add 1. When we go down, we subtract 1, so we get 0 here. It corresponds to the position in the rows minus the position in the columns that we get. So maybe we can do an example of this principle. If we look at the cell module for the partition 1 for the algebra A3. So the possible paths in the Bratelli diagram, I still have it over there. So I can do this path, or that path. So there, I should get a three-dimensional module there. So I have 3 paths. And then the corresponding values that I will get for the juicy Murphy elements acting on the basis elements, or here in the first step I add a box with content 0, so I just get 0. Here I remove a box with content 0, so I will get 1. And then I do the same thing again, add a box with content 0, remove a box with content 0. I'll always get 0 in the first step, which is good because x1 was 0. Then here I add a box with content 1, so I also get 1. Oh, I got, yeah. Sorry. So these are labels from 1 to R, these are labels from, 0 to R, and here 1 to R. So I add a box with content 0, add a box with content 1, and then I remove a box with content 1, which should give me 2. Here I add a box with content 0, I add a box with content -1, and then I remove a box with content -1. -1 plus 1 is 0. So I have 3 basis elements of that one, and up to higher order terms, the action of the Juicy Murphy elements are given by 0, 1, 0, or the other numbers that you get there. So the reason all of this is relevant is that it really helps to compute decomposition multiplicities. Well, I think, yeah, great. No, I'll first move to the next section. Which is about the blocks of this algebra. So to get to know the blocks, we need to kind of have some rough idea about the decomposition multiplicities. So one thing we can observe now is that if this multiplicity is non-zero, then the first thing which we know is that lambda should be included in mu as a partition. We know that the size of mu must be bigger or equal, but you also need to have an inclusion. That's also something which can be obtained from the Littlewood-Richardson rules quite easily, because you start from a symmetric group representation there, and then you add on cups. So you basically tensor with the trivial representation in some sense. So it's not very difficult to obtain that. But now, based on our Juicy Murphy elements, we must have the following. So there should be some path leading up to lambda and some path leading up to mu, for which those numbers that we've just described lead to an identical sequence. Because if this is non-zero, then somehow there is a part of one cell module contained in the other. So if you just restrict that statement to the subalgebras generated by the Juicy Murphy elements, that there must be some common representation, some common one-dimensional representation of this abelian subalgebra. And those representations are, of course, labeled by those coefficients, by the action of each of the generators. So if these have some common constituent as representations over that big abelian subalgebra, there must be some Juicy Murphy, some Murphy basis element with the same action, or in other words, some elements which have those same.
In general, is W lambda not indecomposable?
Indecomposable? They actually are here.
Yeah.
I mean, for cellular algebras and stuff, they don't need to be, but here, oh, yeah, because for R odds, they're standard modules for a quasi-hereditary structure. And in the other cases, it's still close enough that they are indecomposable. Also, it is a general fact for cellular algebras that the cell modules which correspond to a simple module have a simple top. So in particular, they're indecomposable. So it's only the remaining ones which can be tricky, and so there's only one to check here. So this is, yeah. Here it's all right because it's so close to being actually quasi-hereditary. So, for instance, we could have a look at A3 again. So we already know what happens, but we can apply this idea of juicy Murphy elements to prove the inclusion that I said was an easy calculation. So for instance, we could try to prove that these values are 0. So for these two cases, there's only one path in the diagram leading up to it. So here I would add something with content 0, add something with content -1, and add something with content -2. And here I would have two paths. So here I add content 0, add content 1, and add content -1. And here I just reverse the order. First I add something content -1 and then something with content 1. So if I compare these with the possible values I get here, there's no overlap. So when I regard these modules as modules over the abelian subalgebra, I only get simple subquotients which are strictly different from the simple subquotients I get in that one. So there's no possibility to get something in there. And then I claimed that that one appeared. So of course you can't really prove that something appears using these juicy Murphy elements. You can only prove that something doesn't appear. But if you would accept that this module isn't simple, then this is the only remaining chance that we have. And to get that one, there's only one path, which is adding content 0, adding content 1, adding content 2. And that one happens to appear here, of course. So a different path, but some path which has actually the same values. So there is some rougher observation that we can make based on this. Namely the following. If there is some non-vanishing multiplicity, Then this Q partition. So first of all, lambda is contained in mu, so I can look at this skew partition. So I just look at the diagram of mu and delete all the boxes which also belong to lambda. So that one can now be paired up or be paired into pairs with adjacent content. So I mean, the boxes which belong to mu but not to lambda should somehow appear in pairs such that their content differs by 1. And the reason for that is so lambda is some smaller partition, so there must be some path which has equivalent contents. So I must add and remove certain boxes along the way. And that always gives me pairs, because removing a box gave me the content plus 1 and adding it gave me the content. So all the boxes which somehow are added and removed in the path leading up to lambda, certain contents of those should appear in mu. So that gives me some very rough idea to prove that certain multiplicities shouldn't appear. So for instance, I could apply that here to get the answer straight away that this one, for instance, isn't 0. This one must be 0. Because here I have content 0, 1 and minus 1. So if I leave out that one, I get 1 and minus 1. So I can't find a pairing of those two into boxes which differ by 1. So here that wouldn't be enough to show that this doesn't appear, because minus 1 and minus 2 are adjacent. But then you work a bit harder. So this is a rougher but easy to check criterion. So then we're nearly at a point where we have the blocks. Actually, I just need one more lemma, which just proves that certain multiplicities do appear. So I'll write it like this. So I say some simple module appears in some cell module with multiplicity 1 if that partition is actually obtained by lambda by adding 2 boxes in the same row. So an example was, of course, this one. So I just add 2 boxes in the same row. So I won't give the details of the proof, but it's actually quite easy. So this is something which would be hard to prove, something like that for the ordinary Brouwer algebra, but here it's somehow easier, this thing. The theory of juicy Murphy elements is actually more complicated to prove everything, but this is easier. So the idea behind it is kind of the following. If I would start from some Specht module and induce, I just add a cup. So then the little Richardson rule tells me what symmetric group modules appear in here. Because this is basically, as a symmetric group module, the tensor product of this one with the trivial module for S2. So everything which appears here correspond to partitions where I add 2 boxes, not in the same column. So I can add them everywhere, particular in the same row, but not in the same column. And then you wonder whether that actually is a submodule as an AR module, so not just as a symmetric group. So you need to then apply all possible diagrams for the cap and see if you can somehow move back to what generated the module. But the cap is Q-symmetric. So you can again use Littlewood-Richardson to compute when something like this should be killed. Because this should somehow give a something which commutes with a big symmetric group still. That morphism, that idea of going back. And because now this is the sign module for that small S2, it's actually a different rule which applies, which says that stuff which has a chance of not being killed corresponds to adding 2 boxes everywhere but not in the same row. So a lot of stuff appears and also a lot of stuff should get cancelled. But this is the one which appears which won't get cancelled. That's the idea. It's, now that I say it out loud, it's more complicated than I thought. But so it's really to do with the lack of symmetry between the cup and the cap, and just applying Littlewood-Richardson rule twice. So for the Brouwer algebra, this is really what is difficult, because going back, you would have to use the same Littlewood-Richardson rule, and that would say that everything which you created might also get killed. But here, the lack of symmetry says you've created something which you can't kill. So maybe that's a better way of saying it. But anyway, if we accept that lemma, so I think that's a nice complete proof, then we do have the following theorem popping up. So 2 simple modules are in the same block. So the same indecomposable block of AR if and only if lambda and mu have the same 2 core. So maybe I should just mention what the 2 core of a partition is. So the 2 core of a partition is obtained by iteratively removing rim 2 hooks. So basically, for 2 hooks, there's only these 2 possibilities. So I start from some partition. For instance, this one, and I just remove 2 boxes in the same row or column in a way that what remains is still a partition. So for instance, I could remove these 2, and then I can only, I think, remove these 2. I can remove these 2 then, and now I'm stuck. There's nothing of this shape that I can remove. So that's known as a 2 core, and it doesn't depend on the way you've obtained it. So the possible 2 cores are the empty partition, this one, the one that we've created here, etc. So any partition has a 2 core, which is one of these. And so the claim is that the block decomposition just depends on those 2 cores. So one direction of the proof is basically this lemma and the BGG reciprocity, because if I add 2 boxes like that, I'm in the same block. By BGG reciprocity, if I add 2 vertical boxes, I'm also in the same block, by using the BGD reciprocity version of this statement. So one step is really easy. The other step is actually just as easy, because we only need to observe. So let's say this is the lemma, and our Humphreys BGG reciprocity. For this, we just need to observe the following easy verifiable statement. The 2 core of a partition is determined by the following number, the number of even contents the partition has, minus the number of odd contents. So clearly, when I remove 2 boxes like that, or 2 vertical boxes, I don't change this number, because I always add or remove 2 boxes. One will have even, one will have odd content. So it just remains to check that this value is different for each of one of these. So here it's 0 minus 0. Here we just have 1 even content, no odd contents, and now we add 2 odd boxes, so we get minus 1. Now we add 3 even boxes, so we get plus 2. So for instance here, we have our even content boxes, 4 of them, and 2 odd ones. So you'll see this goes on. We never get the same value again, etc. So all the 2 cores happen to have a different value for this number. Okay, so what happens next? So now let's say that 2 partitions have a different 2 core. We need to prove that they're not in the same block. Well, if they have a different 2 core, then I can never have a multiplicity here, because the boxes which appear in one and not the other must be paired into pairs with adjacent content. So each pair with adjacent content is one with an even, one with an odd content. So if they have a different value like that, this condition can never be satisfied. So the only multiplicities which appear are between lambda and mu with the same 2 core. So that gives us the other direction. And shows us the block decomposition. So I think we could stop here today.